Okay, welcome back for this last discussion session. What is the, we have the,
It should start.
we have the
It's just.
session. Ah, okay, sorry.
Oh, you mean the schedule?
Yes, if we have it, otherwise I can.
Well, you stated it's two, right?
Yes, well, we'll split in two rooms now. The discussion session is quite short today, it's only 1 hour. So we decided to have a breakout room part, which is only half an hour, and the last half an hour will be together here. So I thought about two topics. So one will be here, and the other, I think, in
the B room, yeah.
In the B room over there. And the first topic is about large scales versus small scales, again. In this case, thinking about how can we couple small scale studies of dynamics of black holes and large scale simulations where the dynamics, as we saw, is very hard to model appropriately. And for this, I need a facilitator. Any volunteer? Don't be shy.
What's the second topic first?
This, you're right.
Because I can't.
Yeah. The second topic instead is about what we can say about merger timescales and recoil kicks if there is still a last parsec problem or we have moved to a last kiloparsec problem, and what's next for the future.
What I can volunteer for two.
Okay, so we have a facilitator for two, and for one. I don't know if she's willing.
I can do the first
one. Oh, okay. Thank you, John. Okay, great. So we can split and we'll reconvene in half an hour. So 2:10. Okay, great.
Simulations of large scale.
I can hear so.
The first one.
Yes.
Yes. The second.
So
Room 1 is here, right?
Room 1 is here.
Awesome. You want room 1 on that side? No, I guess we should figure out who's going first. So, like lots of people seem to be staying here. Okay. We should all try to move to one half of the room. So let's all move over here. So.
If it's too large a group, we might split into two. Group number 1. That's okay.
Let's together.
I don't know, we'll see.
Alessandro will be upset.
You don't want to upset Alessandro.
You're right.
Okay, so we need to find a reflector, a speaker, and a. Oh, there's 4. Right?
The recorder.
There's a recorder.
Yeah.
Recorder, yes, thank you. Okay, so who would like to be the recorder? The disadvantage of only having 2 groups. We now have 2 big groups. Recorders.
I can be the recorder.
Thanks, Sophie. Thanks, Sophie. that isn't the worst job. So that was a good choice there, Sophie. Now we have the reflector. Yeah, thank you. Like I honestly think that's the easiest job. So you should have, somebody else should have gone for that, really. Like, I guess people are hoping they don't have any job. So who would like to be now the speaker? I mean, you're experienced.
Let other people have a chance to
Yeah, okay.
volunteer, but if I can, I speak a
So people
lot.
are jumping at the chance.
We could pick a speaker at the end, anyways. We can see what how the discussion evolves, and then we can volunteer a speaker near the end. So Sophie, you're good to record. Could you put your recordings up on the screen? Would that be possible?
Yeah, I can do that in a second.
That would be cool.
I just set up the.
And post the link.
Yeah.
Thank you so much.
Okay, so the discussion point is basically how do we bridge the scales between the small scale dynamics, which are obviously going to be very important and are well resolved, against large scale dynamics, which are very poorly resolved and possibly lead to spurious results if we don't do it correctly. So who wants to off the discussion?
So I thought the result that one of the speakers today talked in the asterisk spread simulation,
Yeah,
showing that
that's
the
true.
relative intermediate regime was
Yeah.
actually relatively good enough to predict the future outcome of the binary merger. That was encouraging for some of us who work on cosmological simulations, and in some sense reassuring, and can have some hope for the future direction.
Sorry, just to clarify, was that the one where there's the resimulations?
There's a resimulation work.
Yeah. No, that looked really
It
good.
was a nice work. And,
Yeah.
during the break, I was actually asking her about the redshifting effect. You know, the resolution scale she was showing about was 1 kilopascal or so, where it makes a transition from this resimulating. But that could actually shift depending on the redshift, right? Because of the expansion effect and losing resolution as you go to low Z. So if you try to do the same thing for lower redshift populations, maybe that transitioning scale could actually shift to a somewhat larger scale as you go to low Z. And I was wondering if that may have some kind of impact on the
Yeah.
But something like that can be applied to many other simulations.
Okay. Yes, I agree. I guess the limitation is that we can't probably do resimulations every time to test our results, though. Like if we're running large scale simulations, then we can't always stop and start and have a resimulation to test that everything's okay. Ideally, what we'd be doing is bringing the learnings from the resimulation straight back into the large scale in some sort of a subgrid modeling way, where you're using the results from the smaller scale stuff directly into the larger scale without having to do the resimulations.
Right.
So you should only have to do the resimulations once, ideally, obviously, and then somehow bring that into the subgrid modeling. That would be the ideal scenario. Anybody else want to add to that?
So, Nyanyi, do you have comments on what you think the limitations are of the way that you did things? Like, are there things on even smaller scales that you're worried about, or like, what would you want like people working on cosmological simulations to be careful about when we use your results for subgrid models?
Just because my simulation is not like so it doesn't account for. I mean, I do try to account for as much inflow, new inflow structures as possible, but if you evolve it for an overly extensive, if you evolve it for like a super long time, then at some point you lose control of all those like inflow of matter, which can affect the dynamics. So that's one thing to be cautious about, like when implementing in cosmological simulations. And also, as I show, actually, like especially at high redshift, we found a lot of mergers happen in like these multiple galaxy scenario in which things are still quite chaotic. So I'm not sure if in that case we can extract a good enough subgrid model, or maybe some probabilistic one is possible.
Yeah, like just I guess for my own clarity. So when you were running your when the original simulations were running, you get all these numerical mergers, right? And then when you did the resimulation, you found that some of them merged, but some of them stalled. And so again, the fractions seem to be, I can't remember, but it seemed like most of them merged, but there was maybe 30% that didn't.
Yeah. Right. That's roughly, so that's for mergers that mostly happen in isolation. Like so we trace the system, the Astrid system down to lower redshift, and then if there's no new infrastructure for isolated systems, the merger fraction is relatively high. So it's as you said, like maybe 70%.
Okay. But so 70% is pretty close to 50%. So you're getting it wrong half the time. Worst case scenario.
Yeah, it's not wrong. It's just like they are significantly delayed. And as I said, I didn't evolve them all the way down to redshift 0. So in the subgrid, like for calculating the merger rate from cosmological simulations, people still account for this dynamical friction delay. So it's kind of already, it could be accounted for like post-processing right now, but the resimulation seems to show that there are more complex effect other than like the Chandrasekhar dynamical friction.
Yeah, that's true. Yeah, like you missed the delay. This is true.
I don't have a question aimed towards you and Yu Ying of, is there a certain point you get to in Astrid where you kind of where you trust the analytic or semi-analytic dynamical friction model up to a point? Is there a certain like condition, whether it's a high density region or close encounter with something else, that you can say this is where it starts to go wrong? Because if you can start off the process with a good semi-analytic model and then something else takes over a little later, when you reach this condition, if such a condition exists, I don't know, that could be a way forward. I mean, just kind of like, because what Astrid doing is clearly better than what Illustris and TNG do in terms of keeping the black holes in their own galaxies for longer. But as was shown earlier, that doesn't necessarily give you the correct merger rates in the end. But like somewhere in between those two, the kind of approximations you make break down, perhaps. And is there some kind of criteria that we can recognize that is where the modeling that you have in Astrid currently stops working, or something along those lines?
You remember Lisa Bortola's morning talk about the limitations of Chandrasekhar dynamical friction?
Partly, yeah. It's kind of like saying, because we have some kind of analytic model for Chandrasekhar dynamical friction, right? And you get stuff spiraling towards the center. When does that become wrong?
Yeah.
This is the question I ask.
Yeah, that is also something that really concerns me. I mean, there were some within the Learning the Universe collaboration, right? There was some work being done on dynamical friction, just from the n-body perspective. And that was kind of suggesting that independent of halo mass, it was always synced to the center. But then that is clearly not what we see in the cosmological simulations. And And I'm always thinking, how much do you have to correct for? It's so hard to know the correct answer, especially for low mass galaxies, which do have these density cores. How much wandering should there be? Yeah.
So basically boils down to getting a better subgrid model.
Yeah.
Right? And it's taking the learnings from the small scale re-simulations and somehow porting them into an improved subgrid model. But how do we do that?
I guess my question boils down to, at what point do we need something new to take over?
Yes.
Or is what we're doing wrong already?
Well, it's right some of the time,
Yeah.
right? But it's when, it's basically trying to understand when it goes wrong, which is kind of your question.
Can we identify in a large scale simulation the point where it goes wrong?
Yes, that you may not be able to because we may not have the resolution to actually identify that point. Right? It's not clear.
I wish Shashank or Magda were in this room because Shashank did the really high resolution.
That's true.
And Magda did the high resolution circumbinary with gas. They're not here. Sorry,
I'll
I
give that
need
the
to,
final classic problem.
Yeah.
sorry, you were going to say something.
No, I was going to say the accuracy of that subgrid dynamical friction model really depends on the accuracy to which you can actually estimate the dynamical friction force, right? So, and that depends on the numerical noise. So if the way I think about it is like if I give in a given region, if I construct a sphere, like what is the definition of that sphere being well resolved? And that's a subjective thing, right? So if I say that, okay, 32 particles, let's assume the standard definition, 32 particles, because in simulations, we say 32 minimum dark matter particles are required to resolve, call it dark matter halo resolve. So let's assume that definition and say, if a sphere has 32 particles within it, then maybe that sphere is well resolved and enough to reliably estimate the dynamical friction force, the unresolved dynamical friction force. Now, if you take that as a definition, if you take a given simulation with a given particle mass resolution, and if you have two distinct halos, a lower mass halo and a higher mass halo, the definition of a well-resolved region is different in those two halos. Because in a lower mass halo, the density is lower. So 32 dark matter particles will spread over a larger region. So if you're having, say, a simulation with a merger criterion, where you're saying, okay, once we fall within that sphere, we just merge the black holes, then in a lower mass halo, the merging is happening at a higher separation compared to a much higher mass halo. So there's that complication as well. So we also have to, first of all, figure out, agree on a definition of what is a well-resolved region in terms of dynamics.
Yeah, I don't know.
And that's where the higher resolution simulations will come into play, right?
Yeah.
And also there's this,
I don't know how you do this
yes,
without doing the high resolution.
yeah, exactly. And the other concern I have is in these cosmological simulations where you're merging at larger separations, so you have a set of mergers and you have hierarchical mergers. So a set of mergers are happening at earlier times and they're forming higher mass black holes based on those instantaneous mergers. And those higher mass black holes are merging at later times. And then we have these post-processing models where we are using this entire set of mergers and evolving them as if they are independent mergers. They didn't come from earlier mergers. But there's an internal self-inconsistency there, because if those lower mass black holes didn't merge at earlier times, then they would not have formed the higher mass black holes to have merged at later times.
No, it'll propagate.
Yeah, exactly. And that calls for, I think, an approach where if we can figure out how to take these post-processing models like Luke Kelly's models and imprint them on the fly. Where we no longer say that we have a type 5 particle which represents a black hole. Maybe it represents I don't know, just like stars, like a population of, not a population, but maybe 2 or 3 black holes, depending on. So you in the simulation, you merge them, but you don't call them a single black hole. Instead, you call them multiple black holes. And then you create some sub-resolution prescription based on these higher resolution higher resolution simulations and treat their dynamics. It can get really complicated very fast because now you have, if you have two black holes, they have one variable. Three black holes, you have multiple variables, so and then it can exponentially increase. But we can figure out ways to simplify them.
Yeah, actually, something that I found heartening was that, like, the stalling that you were finding, Yanni, for example, between the two massive binaries was actually, like you were saying, about 1 kiloparsec, right? That's like around the resolution limit for a lot of cosmological simulations. So, like, even if you were to tag something as like a black hole's particle rather than a black hole particle in the center that actually contains multiple, that's actually consistent with where the multiple black holes would be stalled, right? It's not that like one would be in the center and one is like 1,000 kiloparsecs away. They're actually both in the central region. It's just that they have more complex dynamics going on that would produce like different, gravitational wave or electromagnetic signatures. But they're both in the same region.
Yeah.
Right? Would you say that's generally true, or is there like a ton of wondering how?
I think, didn't you guys, Melanie, Martha, do that with New Horizon? Like, I think they have numerical mergers and then they post-process that to be.
Yeah, it's fully post-processing, right? Like,
Yeah, that's kind of the same thing.
it's the same. So like every time you have like a smaller galaxy getting in your system, then you store like all the black holes are like properties are stored somewhere, and then you can, based on the environment, like the gas densities and all the properties of the galaxy, it's a high resolution for like local region, then can post-process and estimate when those two will merge, and like when those three will merge. And
so like at some level, that's doing what you're suggesting.
Yeah,
You don't really
I didn't know
call it like it's a numerical merger versus a.
Yeah, we can have like two separate log files. One would be like the actual numerical mergers, and then the actual merger with inside that multi-black hole particle.
Yeah,
we can eject black holes based on.
people do that all the time. Yeah. In the context of LISA, for example, when we're trying to estimate what would be the event rates, and people do that. Like in Martha's paper, there is a comparisons between New Horizon, that is a highly resolved small volume, and then the Horizon Agent, that is a large simulation, as you were saying, with like about 1 kiloparsec resolution. So then you can compare like what the number of merger that you would get for the two simulations, and those post-processing delays, like how they would impact the merger rate and so on.
So I think you're right. Like lots of people are doing that, and that's the best you can do at the moment. It does have the negative impact, though, that in your simulation on the fly, you're still not doing. You possibly are propagating errors. This will be a major problem if you have lots of black holes.
That's a major issue.
Yeah.
And you're merging the black hole, right? So you're not like the phase where, in practice, you should have several black holes per galaxy.
Yes,
they are merged, right?
gone.
So you're missing this part of the accretion into the black holes.
Or what impact that can have on the galaxy.
So,
that's all gone.
Yeah.
Exactly.
Also, have you got them close enough to be able to merge?
Well, it's always a
Realistic
numerical
way.
merger. Right? Yeah.
That's
sure.
where the definition of well-resolved comes in, right? We have to agree, okay, at this scales, we can't resolve the dynamics, so we numerically merge them, and then rest is at the mercy of the subgrid model.
The limit between the two, I don't know where that is.
Yeah, that's where the high resolution simulations will come in, like at what, depending as a function of halo mass, if we can figure out
The function of resolution.
Yeah, as a function of halo mass and a resolution, what is the scale? Well, scale in the units of the radius of the gas cell of whatever resolution.
But honestly,
I
don't think this is intractable. I think you would run a bunch of high resolution simulations, and then you would get a subgrid model for that, put it into your low resolution simulation, run it again with that, and you see, does it match the high resolution?
Yeah, that's what I did for the seeding, and we can do that for the
insane.
dynamics. Yeah.
Right. I think that's basically what you would try to do.
Yeah.
And as a first step, I was going to say that would work, but of course it might not work. But you would learn something from it. You would learn something from it. You would learn something from it.
Yeah.
And I don't think that's intractable. Yeah. Ken?
The thing that has not come up at this workshop is the usage of machine learning instead of the subgrid models. And I was wondering what people think about that.
Absolutely. No, it did come up though. We did talk about that.
Oh yeah,
in one of the breakout ones. Yeah. And like, I actually was stopping myself from saying, oh, can we not just
Yeah,
machine learn this
but,
away?
The things like we heard today about the second binary evolution, which has a kind of equilibrium solution, that those final outcome is perfect for machine learning teacher data.
Correct.
Let it run.
Yeah, I
So you would like base, so what would it do, right? The machine learning, like in a way, like you would give it like the properties on the fly of the simulation. Like when the simulation is running,
Right.
you would identify the properties, some
Right.
key properties, and
Right.
then based on your
That's
whatever
right.
algorithms.
Then you can give you the appropriate dynamical friction timescale.
Right.
Then you don't even have to do all these, high resolution calculation, which is already pre-done as a teacher.
You have to have them pre-done though.
Yeah,
You have to like give a training sense. Yeah, you have to do it
So
once.
it's useful right now.
Yes,
But that can
yes,
be actually taught.
Yeah.
To the machine.
yes. And then you have the machine learning algorithm sitting inside the low resolution simulation, and it'll do the work for you.
Is that,
Absolutely.
and for that, I think you would have to let the model learn like some PDE, right? Some evolution equation. It wouldn't be.
Yeah.
So
Yeah.
you're
But they can.
because it was well behaved.
Yeah,
You saw
right.
that movie. Everything was being tracked.
But like that's what a machine learning algorithm will do. It'll learn a PDE.
Yeah.
Well, it doesn't know it's a PDE. It'll just learn. It'll relax to that solution.
But you can, I mean, they're
Oh, sorry.
called symbolic.
You could do that. You could do a physics informed one as well.
Or no, not that, but it's like there are models that can actually get a symbolic representation of the dynamics, basically, from that huge suite of
Yes.
simulations.
Yes.
And that can be baked into your subgrid model, right? Once you have like your black holes particle,
Yeah.
and once it gets to some radius in your this evolution, then you go into the certain binary disk phase.
Yeah.
Isn't this still a separate model though?
It is still a
Didn't you
separate
just
model.
use machine learning to derive your separate model?
Yeah, that's what.
Yeah, pretty much.
Yes. Yeah, like
Maybe I should put machine learning as analytical subgrid models.
Yes,
Right.
versus
Yeah. Yeah.
in inverted commas.
Which one is?
Yeah, like I think it can be nomenclature at some point.
Yeah.
Depends what you want to call it.
So for that, you would need to train, like to perform a lot of like very highly resolution, such as what we've seen, like in different environments, different galaxy mass.
This is
I
true.
think that, yeah, and
We're
see us
training.
realize how do we validate the machine learning model, compare that to a separate model. It's a tricky issue.
Yeah.
Think about that. I think like probably like one strong point of using machine learning is that they can like learn more like lots of how different probability, like it's more representative, like more flexible than the separate models. But still, it lies in how do we validate the machine learning model, like compared to some stochastic prediction of whether
And like on like how many, like 100,000, like you still need to train, right? Like and you need to keep enough zoom in, so then your algorithm, you can test it on the testing set, right? So like, is it feasible to like run that many simulations? Like, I'm wondering like how long is your very highly, it takes some time, right, to run that.
It would, but you don't need to run cosmological simulations to do
No,
it. You
but
could-
like even one very highly resolved simulation, like a zoom in or like a partial zoom in, if you need to run like 100, that's what the TNG is doing, right? They have those like, they run like all those zoom ins,
Yeah.
but
I'm not sure, like, I don't know how complex it'd need to be. I could imagine you to run a lot of like small, basically galaxy mergers. And from that, at a high resolution, and that'll give you a lot of different environments straight away.
yeah, but then if you want to apply it to like cosmological simulation, then you need to cover such a wide range of like.
Yes, environment, yeah,
Right.
you're right, you're right.
Yeah.
But Magda did that. Like Magda's circumbinary, binary black hole merger library is like almost 3,000 pairs that were drawn from the Illustra simulation, and so they all had different conditions that were drawn from a cosmological box, right? So but I mean, the volume that you simulate is quite small. Is your concern that the volume should actually be big enough to capture like galaxy scale inflows? because that would take more computational time. But if I remember correctly, from being in the same group as her, I think it took her way less than a year to run that whole thing. Magda Siwek, she spoke this morning, the circumbinary disk library. Yeah.
Yeah, the thing is, the machine learning algorithm would tell you though. Like it'll find out because it'll learn what's actually important, what's not.
Yeah.
So like
And I think this problem is actually more clean than the star formation and feedback.
definitely the
Because it
feedback.
doesn't-
The feedback, yes.
Yeah.
Feedback is not clear.
Yeah, because it doesn't
Yeah.
spew things around
No.
and change dynamics around it. Right? It's just either merge or not merge.
Yeah. Feedback is hard.
It's cleaner.
Yeah, no, it is cleaner. I
Mm.
think it's not. I think it's tractable.
Yeah.
You know, easy as it.
I guess
difficult
another
word.
type of simulation they
There's
can train
a
on.
third possibility, like cycle, like either merge or get ejected. Then
Ejection-
it will be more complicated.
Yeah,
Like,
ejection
Yeah,
is ejection is a problem because we don't know
And then what velocities?
Yeah, one step at a time. Yeah, but yeah, you're right. No, you're absolutely right. It's true.
Probabilistically, perhaps.
How much time do we have left? Because this is the shorter.
We should wrap up now.
Well-
I've tried to kind of categorize.
Yeah, and I think we need to identify a speaker now.
Yes.
So I don't know. I could pick a random number, right, and then just count people, or somebody could volunteer. How convenient.
A speaker?
Yeah.
Yeah.
So what, wrap up? We're all one group. Do we have to?
Oh, no, we have to go to the
present
bigger group,
to
though.
the other
You have to
group.
present to the
Oh,
bigger
I
group.
came in late, okay.
We need a speaker. Jake? You're so good.
So good at wrapping up.
Sure, okay.
Man, thanks for volunteering.
All right.
Like, yeah, is there any final comments? Because I do think we probably need to wrap it up.
What's the first step? Let's decide on the first
Well, I think it's
next step. Running a bunch of high resolution simulations, create a training data set, then figure out what to
I mean,
do.
I guess you could take like all this.
Oh, go ahead.
No, I was going to say, as a start, you could take all the simulation that has been run with a given
Yeah.
resolution, and it's already something, right? And then based on that, you could try to make a model. I mean, we
Subgrid
have
model would be the
already-
first- a subgrid model would be the first thing.
Yeah, I mean, we have simulations already,
Yeah.
right? So you can explore them, I guess.
But even I would have thought the resimulations that were done with Astrid
Yeah,
would be the starting point, right? As a building a subgrid model from those.
Yeah.
That's where I would, when we're doing this, I would start reading those papers. That's the first thing I would do. And that would be my basis point.
And then you can, I mean, people already have like big suites of simulations. You can just use those as training sets. It may not be as big as we need, but you can see what kind of.
For the dynamics. Like
For the
to learn
dynamics, yeah. And also you can use the simulations like, what's this, Shashank. Like those could be training data sets because they're.
Oh, the ones with the, yeah, the
friction,
in-house stuff.
you know,
Yeah, it's true.
boosting.
Yeah, the bloating.
Then you can compare it to like those like learned models versus the analytic models.
Right,
People should start the camel's black hole from.
yeah, no, like, so this came up as well. No, like, you're absolutely right. I think though, yeah. Because we said that as well about some other thing earlier in the week, a Camel's project for, I don't know, was it seeding or something else? I can't remember. Was it the seeding? Yeah, I don't know. No, I don't think it was the seeding. I'm not sure.
Did we talk about it?
It came up definitely because, like, yeah, the Camels one is almost like the first prototype, and the idea is to, I guess, has come up a few times, is to extend that to different regimes. Like dynamics would be absolutely one of them.
The data set here is actually smaller because I was hearing from her that that you just need to cut out the emerging environment. You don't
Yeah.
need all these IGM environmental data, right? So it's a small, like maybe a few kilopascal cube.
That would be my naive guess as well. Yeah,
Small data set, thousands of them.
yeah, exactly. And I don't think that would, yeah, again, naively, I don't think it'd be super expensive, tractable.
That'd be perfect for the CCA process.
Yeah, exactly. Yes, exactly. But I think one of the outcomes from these things can be kind of, good projects to think about and for people to work on. Okay.
All right.
Happy?
Yeah, thanks everybody.
All right, cool. Thanks a million, guys.
Thank you.
Oh, you're visiting.
Thanks, Jake.
Yeah.
Saved us there at the end. That was amazing. Yeah, I thought we were going to let no volunteers. Go to the rest.
Not a nightmare on the way back.
Oh, nice.
I don't think you can do worse than what happened like this week.
Is that right? Jeez, all right, okay.
Yeah. Well, yeah, it can't be that bad because this time we actually booked a taxi from the airport to the house. This is my partner who did it. So it's in our relocation allowance. Can't mistakenly say
That was a mistake.
Statistically, we rely on one person
in
being
the
bad.
plane with me because
We just wait
you
2
know,
minutes, awkward
so
silence. one
actually no,
person
there's
being
other
bad.
bags. Yeah, that could still go wrong, but it's okay. At least this time.
Well, actually, no, that was volunteering to be facilitator.
Yeah, I'm staying in countryside.
What's your volunteer?
Do you know Eleonora Tsari?
Yeah. Oh, I did, and then no one speaker is like anyone. Literally. Yeah.
Where are you staying?
I'm in Alstad.
Okay.
Near the old bridge. No.
I'm actually 5 stops away from you. Going straight north, like on the 5.
Yeah.
Like Neuenheim, and then it's
Yeah.
Hutchins.
Okay. Yeah.
That whole speaking of where the laptop is.
Find something to do, like some type of
I was very lucky, yeah, because Eleonora was
I-
staying.
yeah,
I just was so
very-
very.
Yeah, so I was like,
She was
yeah.
always, and one of my friends at the CFA used to be an MBA, so she was already on Slack,
Yeah,
and she just sent me that, and then.
that's usually when we do
Weird,
like
somehow still
yeah,
surprised.
Like 2 years ago.
because very distant.
Yeah.
I give colloquium on.
Yeah, no, we bought market, super cheap,
But
landlords
yeah,
are
I was just
amazing.
curious, like.
I'm leaving actually, so you're not stealing. Yeah. Yeah, you as well. Good. Thank you.
And
I appreciate that so much. But yeah, I'm in Heidelberg now, so I'm not so far from you. So if there's a cool conference or group meeting in Paris, let me know. Yeah, I know.
I'm just helping with the organization, not doing anything.
So you just.
Okay, yeah, I think we can start.
Yeah, I don't maybe it's with. Yeah, not just, February and April. I think that I should. Just drop me an email.
Yeah, that would be awesome.
Yeah.
Yeah. Yeah, how much longer?
I can spend it on my
So we can organize my nice.
Okay,
And they're having.
let's start the group discussion. So, and today we go in the right order. We have 2 groups, just to change. Let's start with room number 1. So the speaker.
It's me again. So yeah, we were talking about large scales versus small scales, and how we, particularly on the dynamical evolution side of things. I'll start with some of the many problems we discussed to start with, and then I'll go back towards the approaches we might take to tackle them. So we don't get merger rates out of cosmological simulations without a lot of heavy post-processing and a lot of assumptions. It would be nice to do that in a better way. And even when we do have models for dynamical friction and things like this, the behavior when you resimulate the higher resolution is more complex than that. And how you put that together into some kind of analytic subgrid model is unclear. And so the more questions that come out of that are whether particularly this becomes even more of a problem at high redshift when everything is just a mess and there's lots of chaotic behavior and stuff crashing together all the time and potentially seeds flying everywhere. We don't really know at this point. So we need them to work at high redshift, because then those, if you get them wrong at high redshift, the evolutions that will propagate through and get wronger as you go through time. So one thing we're talking about of like, where do our current analytical models for dynamical friction, where do they break down? It's not completely clear where it is. If you start on kind of on larger scales, you've seen kind of with the work with Astrid, that's a lot better than just pinning stuff to the minimum and letting things merge immediately. But it is missing some of the complex behavior due to the small scales that aren't resolved. So we need to kind of figure out what to do with that. And that led to the question of what does resolve mean? And I'm not sure we necessarily came up with an answer for that, but it will be good to know. But so that the approaches that we thought would be good to take in this case would actually be, well, we want to integrate the small scale high resolution simulations into some form of subgrid model. And the potentially best method to be able to do this might be with machine learning. And kind of, you can think about within the code itself and within the simulations, you can start kind of separating between numerical mergers where the two black hole particles that you have kind of become one, and then you follow binary evolution in a subgrid manner. But the actual even getting to that point, and for that kind of subgrid manner, you can kind of come up with models based on machine learning that way. But also getting to that point, you need potentially quite a large training set. And we've heard a bit about some of the training sets we have of, for example, Magda's large sample of binary disk simulations. We've started to hear a bit about some of the M-body type simulations where you can start trying to track dynamical friction and the effects on top of dynamical friction at higher resolution, smaller scales. So there are some bits of training sets out there in theory. Whether there's enough or not is probably not. But the idea would be to use basically make a suite of these. I think we just, how do we describe it? A camels of black hole dynamics. To probe different galaxy environments, different densities, potentially different resolutions as well, importantly, to basically they'll be able to link what we can resolve in the small scale, in the large scale poor resolution simulations to the actual dynamics that you'd expect if you could resolve these things. And for machine learning, that approach is much more tractable for the dynamics, we think, than feedback, etc. So it's potentially tractable, at least a starting point. Whether it'll work or not, I don't know. But I think that was about where we got to.
Thanks. Any comment?
Yeah, so there was, I think that there wasn't anyone at this conference, so that's why we haven't talked much about it. But the CATU, or CATU as should be pronounced, framework is, giving very, very nice results. We have seen self-consistent triples, recoil kicks. Well, with some, the spin evolution is not there yet. And also recently there was a whole suite of simulations, of dwarf galaxies, showing all the effects that we're talking about. So would it be perhaps possible that this, suite needed for the machine learning is already there, and only, the people working on it were not in this room?
Quite possibly, yes. I would say the one caveat of that is that we also need to think about the parameter space that we want to cover, as in cosmological simulations isn't just dwarf galaxies, for example, but it kind of, with a similar framework and a broad parameter space, I think is probably the way to go. You can start looking into the kind of cosmological boxes to look at the kind of parameter space that you need to be able to sample and to figure things out in that case. But with a framework like that, at least some of the simulations, the high resolution simulations and data exists already, it seems.
I think it depends on the regime as well, though. And so that doesn't have gas, which is a slight problem. Oh, sorry.
It doesn't have gas. Like it's just the end body stuff. But I think in principle, yes, yeah, you could definitely have that as part of the training set, but probably not the whole training set, I would think.
They're adding gas.
They can't add, they're adding it analytically, right? You can't, no, because you can't put SPH particles into it because they're ballistic trajectories. It doesn't work. So they're always limited by that's a hard limitation, as my understanding, right? Yeah. Maybe in the, I don't know. I don't know if they can put a grid in there or something. I don't know. Yeah, maybe not. I didn't think so either, but look.
Sorry.
What I know about this, I remember the talk at the astrophysics working group. They can model the shrinking of the binary, accounting for circumbinary disk evolution, but semi-analytically.
It's analytically.
Yeah.
Yeah.
So this is the only thing they can do.
That's right.
In their code.
In their code, I mean,
You can't put the gas in.
because they cannot put the gases in.
You can take models that are based on proper hydrodynamics, right? Yeah, you can do something between where you run the proper hydro simulations, and then you use those as a subgrid model for larger simulation.
Yeah. One thing might be to couple, for instance, Kechu with, I don't know, the hyper Lagrangian refinement Daniel talked about. This might help, at least for the early stages. But of course, if you want to go down and follow it, there is no way. At some point, you have to stop.
Right.
Yeah, I think the kind of binary formation, second binary disk in large cosmological boxes is always going to be subgrid. But getting a reasonable time frame between a galaxy merger and a binary formation is something that we can work on, I think, and that is probably the direction we should be moving in to try and resolve the kind of larger scale dynamical friction and other effects.
Yeah, like I think,
like you're absolutely right, and I think the Ketu thing could only be a component of that. You would also need a subgrid model based on high resolution hydrosims that feeds into that. But I think Martha's point was the Ketu could also form a basis for some of this subgrid modeling and machine learning.
And I think one of the advantages, according to what Peter told me, is that they made it completely free and modular. So everybody could include it in their code. So that's a great advantage also for the community, because we might use different codes and different models and try to add gas, for instance, to what they did.
Yeah.
Yeah, exactly. So sorry. Speaking of frameworks, the Amuse frameworks, I don't know if many of you are familiar with it. It was started by Simon Portekies-Vart. It's a bit clunky because it's a Python wrapper that combines different codes, but in principle, they have done, for instance, simulations of nuclear star clusters with gas. This was mostly for formation of black holes. But as I said, it's clunky because, it connects two codes with a Python connection that is the bottleneck. But I think that, out there are a lot of interesting approaches that probably were not discussed at this meeting because the people were not here. It depends on who applies to participate. But I think that these are, things that we should consider. I mean, I gave up on Amuse at some point because for my simulations, it's not. I would wait more than 5 years again. But I think that, for some small things where we check just, the results could be an option. So without reinventing the wheel, this was basically my point.
Yeah, I agree. Any other comment on this, or in general on the discussion from room 1? If not, I think we could move to room 2. Speaker of room 2, speakers.
Thank you. So we were thinking about merger timescales and recoil in last parsec problem. So I think I'm going to start with the good news. We all kind of agreed that the final parsec problem is solved. Yes. So there are plenty of reasons for this. I think Elisa this morning convinced us all. But then there's also plenty of other literature to convince us of that. So the final parsec problem seems to be something we're least concerned about, but we've kind of moved on to the final kiloparsec problem. And I think that was largely owed also, for me at least, and I think there are several others in the room, to much of the discussion on dynamical friction today. So we were pretty puzzled that there is actually evidence for a gravitational wave background, because today every single one of the talks told us it's very hard to get binaries to form in the center because dynamical friction is so much harder than we thought. So, so that's one thing we're concerned about. We also talked about wandering black holes. Do you want to say something about wandering black holes?
I'm not expert on that.
Okay.
But,
so we were thinking that they seem to be very good at hiding, but given that it seems to be so hard to form binaries, there must be many of them, right? Because every successful merger, there must be many events where the black holes escape and wander the galaxy. So that seems to be one of the conclusions, that wandering black holes are interesting, but probably very hard to spot. Right? Yeah. Okay, so what else do we say about dynamical friction?
So we're talking about this since we concluded on the last parsec problem is solved, but instead we have this last kiloparsec scale problem. We should really think more about a new model on a more detailed model of the dynamical friction, how we for example, this is going back to the second day of discussion. We should have a more zoom-in model, or using the advantage of SEM to really think about what's going on with dynamical friction there, like the gas and the stellar one, before we use them in the cosmic simulations to predict the merger rate and so on and so forth. Because recently, all the like we see in the talks, what we use for dynamical friction is like Chandrasekhar 1943. Seems really old for a model. So I think it's probably a time that we should really look at zoom-in simulations or SEMs and really think about how we tackle dynamical frictions. And I think that's linked closely to the final kiloparsec problem. It's those there because we really don't know what's going on with dynamical friction at that scale. So that's one of the things we talked about. And we also talk about the recoil. It's probably not that a big factor compared to the escape velocity in the galaxy. Given that if you don't have really crazy misaligned spins at the final stage of the gravitational wave emission, you probably won't have a really super high kick from the recoil. That's something else that we concluded on, that recoil is not going to be too much of a problem.
Yeah, and I think also that you first need to actually get the two black holes to form a binary system so that recoil matters, right? But we're at the point where the final kiloparsec problem kind of prevents us from really fully understanding in which cases that can happen and when it's unsuccessful. So I'm also a big fan of doing Zoom simulations of mergers to better understand dynamical friction. I didn't think about that before today, so thanks. Should we open this up?
Thank you. Any comment on this? No one? I think another interesting aspect of the fact that recoil kicks might be less relevant than originally thought is that if we can keep the black holes close to the center, it would be easier to grow them later. So also after a merger, This might be good news also for the growth of black holes in galaxies.
Yeah, and also to link the black hole masses to the galaxy properties, right? If we keep having black holes that escape the galaxy, then what is regulating the feedback? Yeah, that would be really hard.
And we see massive black holes in the galaxies. So if you expect some mergers to occur, it's a good news if they don't escape the galaxy so often. So because otherwise you need for another one to come back at the center, settle and grow and to explain the correlations. So
Yeah. So when you say last kiloparsec problem instead of last parsec problem, can it be solved by his? You talked about this energy distribution function, the Eddington formulation. That result is that modeling not enough to solve this last kiloparsec problem?
I
Or
think
is there more to that? It depends on what you mean by last kiloparsec problem.
I think our discussion was more like that models such as this cause the final kiloparsec problem, right? Because this gradient, well, why don't you explain?
Yeah, of course, like the dynamical friction in a spherical isotropic system, we have been studying it for quite a while, and the distribution function can explain that. But if you're looking in asteroid and you see like hundreds of wandering black holes, and the fact that the galaxy itself is probably clumpy and non-spherical, then it would be harder to model it with a simple analytic prescription. But I do think that analytic models, especially some of the recent ones, can help with that in bridging the timescales.
The difficulty is due to the complexity and the nonlinearity of the system. Is that correct?
Yeah. And so that's why we were thinking, why don't we run one galaxy merger at high resolution that can give us a really good prescription that helps us understand at least where these really massive black hole binaries come from that, for instance, form a large part of the background gravitational wave background signal, right? At least for these large ellipticals, we should understand how the dynamical friction works after a merger.
Also, we conclude down because in the evolution of the binary, the potential of the galaxy is also evolving. That may also give us some problem, or it may help or disadvantage our merger of the black hole. So it's something else that it's really good to be look at using those domain simulations for SAM.